Assalamu alaikum everyone. My name is Mustafa and this is Group 20. Along with me are my team members Kabir, Mahat, Ahmed and Rahim. Today our group will be presenting our project on predicting used car prices using real Craigslist data. As shown on slide 2, used car pricing is notoriously difficult to estimate because the market is highly volatile, with no clear benchmark for what counts as a fair price. Buyers often worry about overpaying, while sellers fear underpricing their car or creating listings that simply do not sell. This lack of transparency creates a real need for a data driven approach to evaluating used vehicles. In response to this challenge, we analyzed tens of thousands of real listings scraped from Craigslist and built machine learning models to understand what drives price variation. As stated on slide 3, our goal was not to perfectly predict the exact sale price of any car, but to produce reasonable data backed estimates that can guide both buyers and sellers. In this presentation, we'll walk through our entire pipeline from data collection and cleaning through feature engineering and exploratory analysis, and finally into our modeling process using both linear and nonlinear approaches. Now, over to Kabir.
Thank you, Subhan. So we collected our data set from the cable, which includes thousands of real used car listings scrapped from Craigslist throughout the United States. As shown on the slide 5, the raw dataset contains many useful fields: price, manufacturing, models, conditions, year, odometer, fuel, and drive type, transmission, body type, paint color, and even the posting date. And further to enrich the dataset even further, we also merged in 2021 median household income by the state, which helped us to examine whether the local economic conditions influence vehicle pricing. Uh, we even performed extensive cleaning. Columns like county, number plate, and latitude longitude were removed due to extremely low predictive values. After removing the duplicates and standardizing the formats, we filled the missing categorical values with unknown and correcting the numerical types. We engineered the several new features, including car age, derived from the posting year minus the vehicle model year, mileage per year, which normalizes the odometer reading, and eventually total mileage. In later models, these engineered metrics, especially car age and mileage based attributes, became one of the most influential predictors, demonstrating the importance of throughput features engineering. Thank you. Now over to Mahat.
So then we moved on to exploratory data and analysis. As you can see in the graph on slide 6, the data is heavily right skewed, which indicates outliers, especially placeholder price values, such as some prices were zero and some prices were very large. So we dropped these outliers to not affect our linear model. And then we encoded the categorical columns like manufacturer, like body type, using one hot encoding. Our first model was a linear model, linear regression with ridge regularization, in which we used k-fold uh, cross validation to determine the best alpha as the hyperparameter to ridge regularization. The top five features as a result of this model were car age, fuel type, drive type, number of cylinders, and type of car. Although these features do make sense, but we can see on slide 8, uh, the model makes massive uh, prediction errors. The residual error is massive in this graph. And in slide 9, it can be clearly seen that the model severely underpredicts overpriced cars. So these graphs illustrates the limitations of linear models.
Taking on from Mahad, now I'll explain in detail why our linear model was not enough and why it performed poorly. As we can see on the page 10, the residual were centered near zero, which showed that the model wasn't systematically biased, but the extreme spread and the right skewed showed the consistent struggle with the high priced vehicles. Moreover, on the scatter plot, as we can see on the scatter plot, which also highlights the problem. The cluster of high prices car was well below the reference line, which points to a fundamental mismatch between linear assumption and the actual market behavior. One more example is, as we can see from this map, which shows the geographical distributions of the model's prediction error across US states. The red areas showed where model predictions were significantly off, while the lighter areas showed where it performed better. The map highlights that while the model generalized well across most states, it performed poorly in certain regions, which suggested that its accuracy is influenced by regional factor, which wasn't captured by our initial model. Another perfect example is the error pattern bar graph, which further highlights the issue. The linear model effectively captures general trends, however, it makes sharp price jumps in the higher price ranges. The graph shows that for cars priced over 40K, the model error grew significantly, which showed its inability to handle the steep prices which increases in the luxury vehicle market. These factors influence us to opt for a random forest model which handles non-linearity and regional variations much more effectively. And I would like to hand it over to Rahim Faisal Khan now. Over to you, Rahim.
Assalamu alaikum, I'm Rahim. So, we obviously discussed that the linear model was not enough to capture relevant predictions for our market. And to solve this, we moved on to a non-linear model. More specifically, we moved on to a random forest regression model. So, what a random forest model does is it works by training many different decision trees on random subsets of the data, and then it combines the results to essentially get a single better estimate or better prediction. This approach helps reduce the overfitting we see and saw when we did a linear model, and thus improves the overall accuracy. Now we can see that the feature importance bar chart shown here shows how the random forest model captures complex interactions between various variables like car age, odometer, drive type, fuel type, and there are even other non-linear relationships that the linear model could not adequately represent. For our best configuration of this non-linear model, we chose a max depth of 20 and used about 200 trees after, and we got to this through experimentation. And ultimately, this reduced the RMSE to roughly 4,000, all the way up from 90,000 to 4,000. So that's about a 126 or 127% increase compared to a linear model. This shows that this was a huge success, and this is backed by the predicted versus actual plot, confirming how our model actually fits way better than the linear one. And you can see if we go back that the linear one was concentrated around here and was less accurate in its predictions compared to the non-linear random forest model. And it more accurately traces that 45-degree line or the most accurate prediction line that we have estimated. So obviously, once we had trained the model, we had to interpret its results and capture how accurate it was. So one of the means we employed was the SHAP model, which basically gave a summary plot of how each feature essentially influences the model output. And you can see in this plot that older cars and those with higher odometer values, so that those have been driven more, consistently decrease the predicted price, while certain drive types and fuel types actually seem to increase it. So this makes sense. Normally, diesel cars are more expensive. Also, this actually indicates that you see with the cylinder count and other manufacturer categories that the model is relying on features and patterns that make sense. And it's not just based on noise. So, in conclusion, through this project, we were able to build an end-to-end pipeline, which included cleaning, feature engineering, EDA, and eventually modeling on a real KXZ data set. And this showed that we were able to essentially do everything involved in the ML model pipeline. We implemented obviously both the linear and non-linear model with the ridge regression and the random forest, and we were able to identify when the linear model is inadequate and when we have to use a non-linear model. Furthermore, we were able to incorporate other data sets and merge them to create a more holistic and deeper data set, as we did by merging the Craigslist data set with that of the median income we got from the US Bureau. And that's what we did to get a more comprehensive data set. And we were able to identify greater number of features and features with more depth via this method. Overall, we were able to gain hands-on experience with the entire ML workflow, and I think it was a very fruitful endeavor. So I hope you enjoyed the presentation, and Khuda Hafiz.